All right, let's do our second video. This is going to be on differentials. So we start off with f prime of x equals dy over dx. We call dy and dx differentials. And as we did above in the picture above, we did it, and we're going to show you again here. Dx is the same thing as delta x. But when we look at it pictorially, the delta y is the actual change right there. That's the delta y, but the dy goes up to the line. dy comes up to the line. So there is a difference in those values. Okay? The way we get dy is we kind of like clear fractions. We had dy dx equals f prime of x, multiply both sides of f prime, or multiply both sides by dx, and we get dy equals f prime of x dx. That's not really what's going on. Really, that's not like the idea of differentials, but it works. It works well enough, and it works perfectly. Delta y is really the change in the y values. So, like if I call the second point here y2, oh, whoops. Let's put on the highlighter real quick. That's my y2 right there. Y1 is over here. And this is at a. This point is at x equals a. This is at a plus some delta x or dx. So y2 is going to be f of a plus dx, and y1 is going to be f of a. So when we do y2 minus y1, which is what delta is, delta y is change in y, we have delta y is f of a plus dx, and then minus f of a. Okay? So we can see what those two things are. We can estimate, which means using this dy form, dy is approximately, this is approximately delta x for small dx, when dx is small. Wait, I said dy, that should say delta y. Whoops, there we go. That doesn't look like one of my y's. There we go. All right, so let's take practice. Let's find what dy is when x equals 2 and dx equals 0.01. We'll start out with f of x equals x cubed plus 3x squared plus 3x plus 1. When you take the derivative, we're using this right here. That's what we want to do. So we need the derivative, and then we're going to plug in what we have. So we take the derivative. The derivative of f of x is 3x squared plus 6x plus 3. We need an f prime of x, and we're doing it at 2. So that's how we get that. And we're literally just replacing these with 2's here. Okay. So 3 times 2 squared plus 6 times 2 plus 3. That's 12 plus 12 plus 3 is 27. And so when we do dy is going to be, this was my f prime of 2 right here. That's my 27. My dx was given as 0.01. We've got 27 times 0.01, and we get 0.27. Okay? Why don't you guys try this one? We're going to use the same x equals 2 and dx equals 0.101. Try f of x equals sine x. Pause the video while you work and see if you can figure out what dy is. Okay, I'll assume you did. F prime of x is cosine x. And so f prime of 2, because we need to evaluate at the point we're doing, which we had up there. F prime of 2 would give us cosine 2. We're plugging that in. We've got dy equals f prime of x dx, which is dy is cosine x dx. And we plug in 2 and 0.01, we've got, end up with 0.01 cosine of 2. When you're working with trig functions and derivatives, they always need to be in radians. It's always in radians. Always. Okay. Try one more. Try doing f of x equals e to the x squared. We'll do it at x equals 1 here and dx equals 0.2. Pause the video while you try to find out what dy is. All right, I will assume you did it. We need the derivative. So the derivative of e to the any power is itself times the derivative of the power. So f prime of x is going to equal our original f of x, e to the x squared, and then times the derivative of the exponent, times the derivative of x squared. Derivative of x squared is 2x, so we end up with 2x e to the x squared. And we're going to plug that in, do our dy equals f prime of x times dx. So f prime of x was 2x e to the x squared times dx. Everywhere we see an x, we plug in a 1. We plug in 0.2 for the dx. We end up getting 2 times e to the first power times 0.2. Dy ends up being 0.4e. And if you need an actual value, like a decimal value, you can plug it in the calculator. Most calculators are going to make you put in the exponent as 1. I know my calculator will make me say 0.4 e to the 1, but we generally, when we're writing it, we don't write it. Okay? Now let's look at how we can connect the linear approximations to differentials, how this stuff works. So earlier we said delta y was f of a plus dx minus f of a. And we just saw differentials could be written like such. Dy equals f prime of x dx. And we had our function for linear approximation was f of a plus f prime of a times x minus a. Okay, so for small dx, we can say, instead of using a, we're going to use a plus dx. Okay, so f of a plus dx is kind of like doing f of a. We have the linear approximation of a plus dx equals f of a plus f prime of a, and I'm literally, wherever I have an x here, like right there and right there, I'm replacing it with what I got here. Okay? So when we distribute that, well, not distribute, clean this up. The a's cancel, and we get f prime of a dx for that last thing. We got f of a. And so f of a plus dx is approximately f of a plus f prime of a dx. And we're saying for small, like this part is the approximation thing. This is like f of x but instead of doing it at x, we're going to do it at a plus dx. That's what we're doing right there, in case that wasn't clear. Okay, so we got f of a plus dx is approximately f of a plus f prime of a dx, and that's LA plus dx. So we had delta y equaled f of a plus dx minus f of a. What we're going to do is go, okay, we had this, we're going to sub in this. So here we're replacing it with that. When we do, LA dx is this right here. LA plus dx is that right there. So we're replacing that there. Notice the f of a's cancel. And we're left with delta y is approximately equal to f prime of a dx, which is what I got right there. Delta y is approximately equal to f prime of a dx, but notice that's the same form of f prime of x dx, because we're looking at it at x equals a. Okay, so what we end up with is delta y is approximately dy. We're just going to take that bad boy and we're just bringing that shit down because we're replacing it. All right, so delta y is approximately delta y. That's what we were showing up here in the pictures. That's what I said, but now we just showed mathematically that delta y is approximately dy. And where we use this happens a lot when we're doing measurements. Measurements always have an error. If you use a ruler, you only can go down so much. If you're using a digital scale, it only shows so many decimal places. If you're measuring time, the stopwatch only shows so many decimal places on time. So there is measurement errors. We always rounds to the nearest number, so there's always going to be an error. So example, let's say we weighed stuff on a digital scale, and the readout was 26 grams, but the actual grams was 26.1 grams. And the actual thing is it's unknown. We're never going to know what that is because we can only see what the measurement tells us. Okay? It could have been 26.1293 or something like that, something crazy. In this case, A is like 26.1 and dx is negative 0.01. So that when we do a plus dx ends up being that. That doesn't look like an A. Oh, that looks all crazy with the highlighter. Ah! There we go. So this is like the a plus dx is what I was saying, and this is my a. The dx, that part we're off, is called the measurement error. Now, when we plug stuff in, if we plug in a measurement error, the error carries forward to, like, let's say we had f of x equals x squared, but we had some error where we're plugging in x plus the error, like delta x here, or dx. I'm going to call it dx. We're plugging in the dx. We get some error. That's x squared plus 2x dx plus dx squared. The actual part is this. This is like an error. So, and it got kind of bigger in its own way. We start off with a small dx error. Now we've got 2x dx plus another part. So the error carries forward. Okay? I was showing an example real quick. Errors carry forward. And we call that error propagation. Okay? So when we do that, we get, if we wanted f of a, we got f of a plus dx. That propagation, like this was a measurement error right here. This was a measurement error. We call this part that we're off the propagation error. And I showed earlier up here when we had the x squared thing, I showed what that looked like. Okay? So delta y, we got some error. And then we're also going to look at relative error. That's like a delta q, or change in quantity over the actual quantity. And this, since delta q or delta y is approximately dy, delta q is approximately dq. And so we can do relative error as dq over q. And percent error, we call it percent error. It's also doing relative error as a percentage, basically. This is just relative error as a percentage. And we call it percent error. Okay. The book and the notes we had from getting ready, this was our absolute error. Okay. So let's take a look at an example. Let's say the volume of a cube is measured to be 6 inches with a maximum error of 0.1 inches. Let's use differentials to estimate the error in the computed volume. And then we'll compute the volume if the error is below. So 6 minus 0.1 gives us 5.9 inches. Then we'll do it if the error is making it larger. 6 plus 0.1 is 6.1 inches. We'll look at the two estimated errors versus these are like the potential errors. This is what the shape could be. So any error off of these is called the potential error. Okay. Estimated error is going to come from differentials. Okay. And then we'll find percent error. So we're going to call the side S equals 6. I'm going to use S for side. The error can be plus or minus 0.1. So I'm going to say my ds, which is the thing like this is my delta S. It can be between negative 0.1 and 0.1. So we start over here on the left. Volume of a cube is side cubed. And if we take the derivative and do the differential version, we got dv equals 3s squared ds. Well, I have the ds here and I have a ds here. If I want to make this look like this, I got to multiply this by the 3s squared. So I'm going to multiply by an inequality by 3s squared right here. Okay? So I multiply by 3s squared. I'm plugging in s equals 6. I get my possible change in value, my estimated change in volume. The error could be between negative 10.8 inches cubed and 10.8 inches cubed. Then we're going to look at the actual volumes. We're going to actually do the volume at if the perfect cube, 6 inches there. But we're going to look at doing what it said with the 5.9 and the 6.1 as well. The actual volume at 5.9 would be 5.9 cubed. Throw that in a calculator, you get 205.379 cubic inches. V6, a volume of 6 inches. 6 cubed is 216 inches cubed. And V of 6.1 is 6.1 cubed is 226.981. And our absolute error, again, absolute error here. We talked about it as being measured minus true in our getting ready. Measured is like the actual value, and like perfect would be the perfect square. That's the true value we're looking for. That's my measured. That looks weird like that. I'm going to write a little bit better. Measured minus true. There we go. So if we do that, the potential error, like the 5.9, that's when we're using like a negative 0.1 dx. We're on the left side. We do the actual 5.9 cubed minus the perfect value, we get negative 10.621. And my potential error, if we go overboard, if it's the errors on the positive side of 0.1 dx, we get 226.981 minus 216. Yeah, that gives us 10.981. So up here we had our error in volume estimated. This would be the actual, what we just calculated right now. These values are these end up being my delta V. We had dV up here, delta V down here. And so if you compare the two inequalities, they look pretty close to each other. Look at that. I pulled that one there and I put these together to make this. Those values are pretty close. If we take a look at doing percentage error, we take the absolute error, the actual error, and divide by the true value and multiply by 100. But we're not going to do absolute because absolute, remember, what the difference was with the absolute is absolute error did absolute value. So we're not going to do the absolute value. We're just going to keep the error as is, plus or minus. So we got negative 10.8, which was my dV. We're going to do, like I said, we can do dV over V. Up here we said we could do dQ over Q. We're doing dV over V here. Oh, that should have a V right there. So we're doing dV divided by V, negative 10.8 divided by the actual volume, and then positive 10.8 divided by the actual volume. When you divide that, you get 0.05. That would be my relative error. If we do it as a percent, we multiply by 100. We get negative 5% is less than or equal to dV, should say over V, which is less than or equal to 5%. So my percent error is plus or minus 5%. Now this came up today when I was talking with one of our students in class. He had just negative 5 and 5. When you're doing percent error must have the percent sign. The percent sign is important to indicate percent error. Without the percent, it looks like you're doing relative error, and it looks like it's off by 5, which would be 500%. So you definitely want to have the percentages in there. Okay? And that's it for this video. Peace.